So we would like to break down to you just a few points from AI Day 2, so let's jump in. Feel free to subscribe for more details because we will be explaining how this bot was designed similar to the marvelous design of the human body.
Hello.
At the beginning of this show that was aired on September 30th, Elon Musk started off with a brief introduction encouraging everyone to take their seats as he introduced to them the first visual of the prototype, which is Bumble C.
All right. Great. Welcome to Tesla AI Day 2022. We've got some really exciting things to show you. Should we bring up the bot?
One little bonus tip for the day. This is actually the first time we try this robot without any backup support. Cranes, mechanical mechanisms, no cables, nothing.
Yeah.
I wanted to win with you guys tonight, but it's the first time, so let's see.
You ready? Let's go.
Go.
I think the bot got some moves too.
The robot was able to walk out smoothly and accomplish its task, and it walked off into the distance into that virtual background. Then they showed the next slide of a few of the other actions that they were able to train it to do in the following slide.
Just humble beginnings, but you can see the autopilot neural networks running as is, just retrained for the bot directly on that new platform. That's my watering can.
Yeah. When you see a rendered view, that's the robot. That's the world the robot sees. So it's very clearly identifying objects. Like this is the object it should picking it up. Yeah.
We use the same process as we did for autopilot to collect data and train neural networks that we then deploy on the robot. That's an example that illustrates the upper body a little bit more. Something that we'll try to nail down in a few months, over the next few months, I would say, to perfection.
This is really an actual station in the Fremont factory as well that it's working at.
Yep. So.
Next up, Elon revealed the second version that they designed, which is Optimus.
What you saw was what we call Bumble C. That's our sort of rough development robot using semi-off-the-shelf actuators. But we actually have gone a step further than that already. The team's done an incredible job. And we actually have an Optimus bot with fully Tesla-designed and built actuators, battery pack, control system, everything. It wasn't quite ready to walk, but I think it will walk in a few weeks. But we wanted to show you the robot, something that's actually fairly close to what will go into production, and show you all the things it can do. So let's bring it up. So here you're seeing Optimus with with the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom, so it has opposable thumbs, and both left and right hand, so it's able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible, and ultimately millions of units, and it is expected to cost much less than a car.
I'll just bring it directly to the right here.
I would say probably less than $20,000 would be my guess. Done a great job. I'd just like to give a hand to the whole Optimus team.
Today, let's do a quick timeline recap. So last year we unveiled the Tesla Bot concept, but a concept doesn't get us very far. We knew we needed a real development and integration platform to get real-life learnings as quickly as possible. So that robot that came out and did the little routine for you guys, we had that within 6 months, built, working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here. So this guy is rooted in the foundation of sort of the vehicle design process. You know, we're leveraging all of those learnings that we already have to take this product to scale eventually. How are we going to do that? Well, we're going to reduce our part count and our power consumption of every element possible. So now that we have our sort of core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well.
What the robot to do. These tasks are picking up boxes, turning, squatting, walking upstairs. Whatever the set of tasks are, we can play to the model. Robots, these are actually the modal behavior, the first 5 modes of the robot. And typically, when people make robots, they make sure the first mode is operant. Biology is non-linear. This matches it quite accurately. So that's a representation. The 4-bar link is obviously not physically a 4-bar link. As I said, the characteristics are similar. But me bending down, that's not very scientific. Let's be a bit more scientific. We've played all the tasks through this graph. And this is showing picking things up, walking, squatting, the tasks I said we did on the knee. You'll see it go transparent in a second. You'll see the 4-bar link there. It's operating on the actuator. This is determining the force and the displacements on the actuator. I'll now pass you over to Konstantinos, who'll tell you a lot more detail about how these actuators are made and designed and optimized. Thank you.
Thank you, Malcolm. Important thing that matters here is energy, mass, and cost. We are carrying over most of our designing experience from the car to the robot. So, in the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive cycle. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. The actuator in particular has a mechanical clutch integrated on the high-speed side, angular contact ball bearing, and on the high-speed side, and on the low-speed side, a cross-roller bearing, and the gear train is a strain.
There was a nice demonstration of how powerful the actuators actually are.
A half-ton, 9-foot concert grand piano. And this is a requirement. It's not something nice to have, because our muscles can do the same when they are direct driven. When they are directly driven, our quadricep muscles can do the same thing. It's just that the knee is an up-gearing linkage system that converts the force into velocity at the end effector of our heels for purposes of giving to the human body agility. So this is one of the main things that are amazing about the human body. And I'm concluding my part at this point, and I would like to welcome my colleague Mike, who's going to talk to you about hand design.
We're also incredibly dexterous. that we may have never seen before can be grasped by the human hand and by our robotic hand as well. The converse there is pretty interesting because it's saying that these objects are designed to our hand instead of having to make changes to our hand to accompany a new object. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller, which drives the fingers and receives sensor feedback. Sensor feedback is really important to learn a little bit more about the objects that we're grasping, and also for proprioception. And that's the ability for us to recognize where our hand is in space. One of the important aspects of our hand is that it's adaptive.
Next, they showed the similarities between the Tesla bot as well as autopilot in all of the Tesla vehicles. And it really helps us to see that they're building upon their platform.
Reported directly from autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the autopilot team that the bot might have to interact with its environment. And we're using those points to get a better estimate.
Next, there was a demonstration about walking.
Don't fall. And of course, also coordinate the motion of all of your limbs together. So now, plans are good, but we also have to realize them in reality. Let's see how we can do this.
Pieces we need in order to close the loop. So we use our better bot model. We use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect that reality is doing to us in order to add corrections to the behavior of the robot.
Location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance its location. Then our optimizer will create this trajectory instead.
Right, so hopefully by now you guys got a good idea of what we've been up to over the past few months. We started having something that's usable, but it's far from being useful. There's still a long and exciting road ahead of us. I think the first thing within the next few weeks is to get Optimus at least at par with Bumble C, the other bot prototype. All components needed to scale this product up. But I don't know about you, but after seeing what we've shown tonight, I'm pretty sure we can get this done within the next few months or years and make this product a reality and change the entire economy. So I would like to thank the entire Optimus team for all their hard work over the past few months. I think it's pretty amazing. All of this was done in barely 6 or 8 months. Thank you very much.
This is a new channel, so feel free to hit the like button, and Cyan, our AI support, let us know what to do.
Hit the like button because we unlock updates that make you go woo.
That's right, Cyan. And subscribe because we have more updates coming for you.